So first of all, if you have a normal distribution, your shape should look like this. It is single peaked and bell curved, and the area under the curve is 1. So anytime it's normal, in stats we'll write it like this. So you have normal, capital N, that just means the distribution's normal. This lovely symbol, it's like a cursive U, all right? Little extra tail right here. This means the mean, and this guy's called sigma. So this is mu, that's how you actually say it, like a cat, mu, and this is sigma, that's the name of the symbol. But this stands for the standard deviation, which is really just the measure of spread. This is a calculus formula. It is an integral. You don't need to know it. It's basically just telling you that if we integrate, the area under the curve is always 1, all right? And then we have the effect of sigma. So what happens right here to my curve? So here sigma is 0.1, and then it's 0.2, and then it's 0.3. So if your standard deviation increases here, then this guy gets flatter. So the smaller the standard deviation, the taller and skinnier it is, right? So the more spread you have, the more spread out the distribution is. Another cool thing about the normal distribution is it always is distributed similarly. So, for example, if you're talking about the SAT, they always put it on a standard curve. And your average here, or your median's at 500, and 68% of people will always score within 1 standard deviation above and below the mean. Okay, and if the standard deviation is 100, that means that 68% of the people will score between 400 and 600. So you want to memorize this rule of 68%. So this is saying that 1 standard deviation above and below is always 68% of the data. If I go 2 standard deviations above and below, that will always be 95% of the data. So if I did 2 below, that would be 300, and 2 above would be 700. So that means that 95% of people are going to score between 300 and 700 on the test. Okay, and the last one is 99.7%. Okay, and the book originally teaches this as 99%, but I don't know why, because it's supposed to be 99.7. So in stats, if you go 3 standard deviations above and below the mean, that is always 99.7% of the data. Okay, so almost all the data will be within 3 standard deviations of the mean. We're going to calculate these on our calculator. So first of all, the mean weight of babies in 1970 was 6.8 pounds. That's how much my kid was, 6.8 pounds. Right, on target, all right? With a standard deviation of 0.8. If the distribution of weights was normally distributed, what percent of babies weighs less than 6.4 pounds? First, before you plug it in, we're going to draw the curve. So you're always going to sketch a picture, and you're going to shade. So draw yourself a little normal curve right here. It doesn't need to be great. Just a little curve, right? And right in the middle, I'm going to always put the mean right in the middle. So this one is 6.8 pounds. And then if I add 0.8 3 times, I can write that up here. The next standard deviation above, I would add 0.8. But what are we trying to find? The distribution was normally what percent of babies weighed less than 6.4? So 6.4 we would say is right about here. And we're going to shade to the left for less than 6.4 pounds. So what percent of them weighed less than 6.4 pounds? So we're going to go to our calculator. And where is it? Thought I opened it. Maybe not. All right, you guys, so we're going to go to calculate. So you're on your blank screen. And then everybody go to menu. And then go to statistics. And then go to distributions. And then go to normal CDF. Always do CDF, that's a cumulative or a shaded area. And I just scrolled back up to PDF. All right. So your lower bound is a really, really small number. If you plugged in 0, that would work. You can't really have a negative birth weight anyways. But anytime you're doing a lower or upper bound, we always just plug in a really low number, a really high number. However, if you plugged in 0, that would work. But I'm going to do like negative 10,000 just to get you thinking. It's always something really small. And my upper bound, we were shading up to 6.4. We wanted to know babies, what percent of babies weigh less than 6.4 pounds. And then my mean, that's the mu right there, was 6.8. And my standard deviation is 0.8. They gave us that, so you plug it in. And then you press OK. All right. So that gives me 0.385, blah, blah. So that's the percent. Always move the decimal 2 over and round to 3 decimal places. So that'd be 30.854%. However, this is what you have to write to get full credit on the AP Stats exam. Therefore, you're going to have to write this as well. It's still really easy. You need to write norm CDF. And then your lower bound, which if you put 0, that would be fine in this case, or negative 10,000. Your upper bound is 6.4. Ran out of space here. And then mu, your mean, is 6.8. And sigma, your standard deviation, is 0.8. And then you can put equals your answer. Okay, what percent weighed between 6 pounds and 7 pounds? Well, we were going to do this in our calculator, norm CDF. And if I drew it, we had 6.4 or 6.8 was our mean right here. So 6 pounds is somewhere over here. 7 pounds is somewhere right here. And we shade the area under the curve. So norm CDF. This time, you guys, what's my lower bound going to be? It's 6. Because we're going from 6 pounds to 7 pounds. So my upper bound is 7 pounds. And my mean stays the same at 6.8. And my standard deviation is 0.8. And you guys plug that in and tell me what you get. Fabio. It's basically, we were shading to the left. So anything, you pick something really small. Yeah, you could have picked 0 because that would make sense for weights. But yeah, if you're doing up, you would say like some number up to 10,000. We'll probably do the next one that way. Yeah. Is there anyone, did you figure out how to do it, Aaron? Okay. With the 84. Good. You got the directions on there. All right, anybody got me a percentage for this one? 44.005. Is that what you guys got? All right, awesome. So that's the percent of babies that weigh between 6 and 7 pounds. All right, how about more than 7.2 pounds? So here's 6.8 right in the middle. More than 7.2, we'd shade above 7.2. These graphs aren't big enough. I need more space, but that's all right. So now I've got norm CDF again. And this time, what's my lower bound going to be? This time it's 7.2. And my upper bound, because I'm shading to the right here, is some really big number, like 10,000, even though that would be a ridiculous weight of a baby. You can still plug it in, all right? And then our mu is 6.8 again, and our sigma is 0.8 again. So what percent of babies are bigger than 7.2 pounds? Did you guys get 30.854? All right, what if they asked, what percent of babies weighed exactly 6.8 pounds? That was a really bad normal curve. Okay, exactly 6.8. Is there any area, if you're doing an exact point under the curve? No. So you can never do these when it asks for like an exact weight. It has to be a range because we're talking about an area. So you can just be like 0%. Because there's no area there at one number, all right? Same with that 6 point, that one or that one. So it has to give you a range in order to use norm CDF because you're finding an area under the curve. Any questions?